Alright, welcome to another lecture of electronic circuit and design. And previously we constructed a circuit related to the class C amplifier, in which we claimed that the circuit is having the 75% efficiency. Alright, now today we are going to use the same class C amplifying circuit, but with little bit some modifications. As we know that previously, when the output was observed with respect to this class C amplifier, it was expected to be sinusoidal, but practically the output was some way similar to that of the digital circuit, and its output can be observed in the form of a binary, where you can see that either the output is at maximum 24 volt or is at 0 volt. Okay. Alright, since the class C amplifier is not expected to be a linear application even for the resistive circuit, so therefore it is necessary to convert this output as an sinusoidal with respect to the input signal. In order to do that, we need to attach a tank circuit that is made up of the LC combination known as the resonant circuit, and whose frequency can be evaluated by the FR is equal to 1 over 2 pi under root LC, which can be accomplished by equalizing the inductive reactance to that of the capacitive reactance, and you can easily fetch the resonance frequency formulation. Okay, now what happens at the resonance is that the circuit gets open, and there is no more current that can flow toward the other side from this tank circuit. Okay, now this circuit is actually representing the class C amplifier with that of the resonant tank circuit. This one is the LC parallel circuit that is known as the resonant tank, and this is the input voltage, and which we have fixed at 500 hertz. And if you solve this parallel network, you will be able to find the resonance frequency, and for this values 1 micro capacitor and the 25 millihenry inductance, the resonant frequency is at 1000 hertz frequency. Okay, one of the major advantage of using this circuit is that it serves as a frequency multiplier. Now that means that whatever the frequency that has been fed at the input, and you need the amplified version of the output signal, so whatever the frequency is being fixed by the resonant tank circuit, the output signal will have the same frequency. Now that means if currently with respect to this circuit, if we have the 1000 kilohertz frequency generated by this tank, and the input is the half of that tank frequency, that is 500 hertz, so the output voltage will be having the double frequency with that of the input. That means the frequency of the input signal has been multiplied, and it's actually equal to that of the resonant frequency. Alright, now you might be curious to know that you are giving the DC input to the positive loop of this resonant tank circuit, and you have studied that the capacitor blocks the DC as it gets fully charged and it becomes open, while on fully magnetizing the circuit, the inductor becomes short. So how you're going to work? Basically, we will be providing the alternating voltage by the help of using this transistor that is continuously switched with respect to this input voltage which is an AC voltage, and the capacitor and the resistor are being used as a clamped circuit, where the diode in this circuit, in this loop, is being used with that of the transistor between the base and emitter junction. So this is that is another thing. To conclude this, that over this circuit, we will be providing the alternating signals on the positive and negative, and that will be done by our transistor by controlling its switching frequency or the switching modes. Now let's see what happens when the transistor gets to the conducting state, and what happens when the transistor is in off state. Alright, now what happens in the phase 1? In the phase 1, when the transistor gets on, the positive voltage from this terminal will start to move into the loop, and it will start to charge the capacitor at the maximum voltage of VCC. Now in phase 2, when the transistor gets off, the capacitor that is being charged will now start to discharge through the path of the inductor, and the current will start to magnetize the inductor till the point will be reached when all of the energy from the capacitor will be transferred to the magnetizing phase, that is the magnetizing the magnetic field, the energy that is required to fully magnetize this inductor. Alright, now in phase C, still the transistor is in off state, and as the capacitor has fully magnetized the inductor by transferring all of its energy into that magnetic field, and it is completely discharged, now the inductor will start to discharge its energy from the other side, and this energy will be once again be transferred to the capacitor in its charging phase. But note that this time the overall energy that was transferred by the capacitor to that from the capacitor to the inductor, and now the inductor has now once again charged the capacitor, the magnitude between both of these energy will be different. Now that means the sum of the energy has been dissipated due to the resistivity of the internal wire of this inductor as well. So that means that in the second time when the capacitor has been charged, this time it will be in the lower voltage as compared to the previous state. While all of this process is being happening, this form of state is actually called as a flywheel effect. And you might be noticed that the voltage that is being transferred over that the capacitor will be some way just like this thing. This is known as the damped oscillation, in which the oscillations are being decreasing in magnitude with respect to time. However, it is also claimed that the type C class tuner circuits are 100% efficient. Now previously in class C amplifier, when we were not using it as a tuning circuit, without the resonant circuit, the efficiency was 75%. And using this mod, in which we expect that the output voltage will be sinusoidal with respect to that of the input voltage, the efficiency of this tuner circuit, or with the help of this resonant tank, the overall efficiency will now be approximately 100%. Alright, now we can easily calculate the efficiency of this circuit by just using the useful derivations of some formulas. We need to find the output power, and output power is in this case is equal to 0.5 times of VCC square divided by RC, where RC is the equivalent total impedance of this parallel circuit LC combination. Okay, now the power dissipation, as we have also evaluated this factor from this lab number 10 when we were actually justifying the class C amplifier circuit, where it's actually equal to the duty cycle, which is the on time divided by the total time, and multiplied by the saturation current and the ICE, and the saturation value of the voltage for collector to ammeter VCE. And simply by just using this formulation for the output over input power multiplied 100, you can easily find out the efficiency. Now here in this case we have the parallel network, the capacitor and the inductor. C is equal to 1 microfarad and L1 is the 25 millihenry. So just in order to find the total impedance, it's actually equal to the RC, that is the Z total. And for the parallel circuit we need to find the admittance which is reciprocal of that of the impedance. So in term of the capacitor, the admittance or we can say the capacitor has the susceptance that's equal to 1 over XC, and the susceptance of the inductor is actually equal to 1 over XL, and the total the admittance is the sum of all the components in the parallel 1 over XC plus 1 over XL. If there was any of the resistor, that will also come 1 over R. Since it is absent in our case, so we can ignore it. Okay, now Z is equal to 1 over Y. For YC is the imaginary component multiplied that of omega C, and YL is the negative J over omega L, and Y total is equal to YC plus Y of L. And you need concern with the magnitude, so you can easily find it by the squaring the terms of the real components plus the terms of the imaginary components. Since you have only imaginary component present over here, so you can easily place the values over here. So it will be equal to the omega C minus omega L whole square, and it will give you the total impedance. If you place the values of this capacitor and the inductor in it as well, so you will get Z is equal to 104 ohms. Alright. Okay, now the output power which we can obtain from the circuit is that we have the 24 volt DC battery that is connected with the collector side. So if I place the values over here, 24 square divided by the RC, that is 104, I will get the output power is 2.7 watt. So now let's just calculate the power dissipated over here. So when I just simulate the whole circuit to find the power dissipation, so I need to find the value of the turn on and turn off. So this is my input signal and this one is my current. I need to check what is the on and off time so that I can calculate it. Okay, this one is the green signal is representing the input voltage, and you can easily see that my conduction is at 90 degree, and I can easily calculate my on and off time. Since my frequency is 500, so 1 over f will give me the total time, that is 2 millisecond. And let's just calculate the on time by clicking on name. I will get one of the cursor, and this one is the on. It's approximately 2.257 microseconds. Okay, so approximately you can place it in that value as well. Now find out the duty cycle. Okay, I have now just placed the formula for the power dissipation. It's 0.2 on time millisecond, and 250 microsecond can be converted into millisecond, approximately 0.2. It should be like. So the on time is 239 on exact. It's a microsecond, so we can also write it as 0.23 millisecond as well. That's why I written here 0.2 millisecond on time divided by the 2 millisecond, that is our overall total time. So let's check for the ICE saturation and VCE saturation. Okay, now let's just find out the value of IC, the collector current and its saturation value, and as well as the collector voltage and its saturation value. So this is the collector voltage probe, and if you move the cursor a little bit closer to transistor, you will get this shape of the ammeter where you can measure the collector current. Just press it over here, and let's move towards the tab where we have two values. The green one is the representing the collector voltage, and if I click here for the cursor, this is my let's find out the saturation point. This one is this that's one in the first 37 millisecond before we get this point over here, and it says that minus 10, that's in the negative direction, and it's 10.9 millivolts. I hope that you remember the simple circuit of the class C amplifier whose output was represented in the digital form. There was you find out that value by just clicking the moving your cursor toward the minimum value of the collector voltage, and ideally it was supposed to be 0, but it's never always just like that. So it's over here is minus 10.9 millivolts. This is our collector to ammeter saturation voltage. Now for the collector current, it's represented by the blue waveform. So we can choose our respective cursor by clicking on to that mark, and the point where it was maximum, we can have some value at the same point near to that. It's exactly 146.19 milliampere. Okay, now just try to plug all down those values that you have evaluated from the output and the power dissipation to find the overall efficiency of your circuit. So efficiency is the output power, that was 2.7. The input is the equal to the output power and the sum of all kinds of losses in your circuit. So since we have only one power dissipation, that is being 1.4 milliwatt, and the overall efficiency is 99.9% of the circuit, so that's nearly 100%. So let's now check it out for the last phase, that how does the output looks like when we say that this circuit is an frequency multiplier. Okay, now let's just simulate the circuit and press the button. This one is my input signal, that's 2 volt and 4 volt peak to peak, and over here it's being clamped, and with the help of the clamped voltage, it's you can easily see that the voltage that is being provided toward the base to emitter junction is now at max 3 volts at the negative side. It's negatively clamped, and this is equal to the 2 volt and plus the 0.7 voltage of that of the from that base to emitter junction diode. And when you sum them up, and in the positive cycle, when the voltage is being supplied, the diode gets forward biased, and the diode is this capacitor gains the voltage of approximately 0.7 volts, and when the negative cycle moves toward it, the overall voltage get clamped. I hope that you remember it when you were studying electronic devices from that book. And now let's check the output. This one is the output, and if I zoom it over here, and you can easily see that the input voltage, the frequency of input voltage is 500, and that of the output signal is having the twice the frequency that of the input. And also it is being cleared that whatever the frequency that is being provided by the resonant tank circuit, the output will be having the same frequency. Okay, now let's just perform one test, that if I decrease the frequency to 300, will there be any kind of change at the output or not? Let's just run this simulation again. Yes. We were talking about the damped oscillations. If you can see that in this figure, first of all, the first spike when the capacitor was actually being charged, and the next of the amplitudes have been gradually decreasing. This is the first, this one is the second, and this one is the third phase having much more lower energy. This one is the fourth one having one time again the lower, and so on, till if I extend it up, the time will reach when the whole process will become in a steady position. So if I simulate it for the prolonged time, let's see what happens. Let's say 120 milliseconds and simulate it once again. Okay, fine. So this means that the outputs are having several jumps in it. You can easily see the first thing, that the frequency is doubled. Secondly, the effect of damped oscillations after regular interval of time, in which the capacitor was being charged, secondly it was charging the inductor, and thirdly the inductor was feeding the energy to the capacitor once again, but the magnitude of that energy was each time lower as compared to the previous state. So that's why the first spike is at the 150 volts. However, at the second, when these oscillations be damped, its amplitude has been decreased towards at the level of 46 volts, and after that in the third level it's 37, and in the fourth level it's 32, and fifth and sixth it's 28.6. so that means the oscillations are actually dying out with respect to the time, and after these oscillation completely dies out, you will get the average amount of the voltage. That is, let's say this is the packet of our received signal, and it's having the RMS value of 29.448 volts. So that means on average the voltage will be 23.8, and the magnitude of the damped oscillation will be decreasing with respect to the time. So okay, now in third phase we can also perform some sorts of experiments for our testing point of view, in which we can connect the DC battery with this resistor and check its impact on the output voltage. I hope that you might have heard the word of modulation, over modulation and under modulation. Now let's see whether we can go for that phase again, because we are having some resonant tanks in our circuit. So let's do the test, that how we can change by changing the voltage at this base level. Can we perform, or can we get some modulated output or not? This is only for your interest. It's actually nothing to do with this class C type amplification. Okay, now if I connect my DC battery with this resistor in the negative direction, and provided with a 0 volt, I get the same result as it was before. Now if I just apply 0.5 volt, now that means that I am actually opposing the my base to emitter junction diode. Now let's see how it actually behaves. Okay, now if you can observe that there are clear signs of resonant voltage, that means if in the beginning the spike is very high and after that it's now lowering up, lowered again, and these are the clear signs of the damped oscillations that you have actually seen from this table, from this picture V of R. Now if I increase my voltage once again to 0.1 to approximately 1, now let's see what happens now. Now although there are oscillations, but you might be observing that the frequency of oscillations have actually increased. Before this 1 volt, when we were actually observing our voltage, this is the first level of the amplitude, this one is the second one, and this one is the third level. You can see this one is the third at nearly 9.5 millisecond. This one is the third. If I move back once again 0.5 and re-simulate it again, now this one is my first level, this one was my second, and the third is somewhere at 36 at about 36.4 volt, but the time is 23.64, and that means the time is larger. It also means that the frequency will be low. Now if I start, that actually concludes the overall discussion, that by increasing the negative voltage over here will increase the frequency of the damped oscillations. So if I increase to my 1.5 volt over here and just re-simulate it again, now you can easily see that this type of modulation, although the amplitude has also reduced, that means that the transistor is not getting the complete time of switching. Therefore the voltages are not able to be properly switched between 0 and 24 volts. So it's also clear, and also the frequency of the oscillations have been increased as well. So I hope so that you might have enjoyed this lecture. If you have any questions, just comment in that section, or you can ask me in the email that has been presented in the description. So you are most welcome to ask anything. So I do hope that you might have concluded that the class C type amplifier with the tuning circuit are much more highly efficient as compared to all other types of the classes that were A, B and AB. Okay, so thank you very much.